Hello everyone. Welcome to this lecture on advanced fluid mechanics. Today we are going to talk about Stokes flow. Basically, these are the flows where Reynolds number is very small and the flow is usually very slow. And throughout the lecture, we are going to refer back to one of the pioneers of fluid mechanics, Sir G.I. Taylor. So you might already know about him from some of the previous lectures and also from some really cool dimension analysis exercises. However, in this lecture, we are going to focus on the part of his work which he did with viscous liquids. So, in that spirit, let us begin this lecture by looking at some of the videos which he used for teaching. So, the next voice that you will hear will be of Sir Taylor.
Pulling a knife from a pot of honey, for which mu is very large, demonstrates two properties of a viscous fluid. It can resist both tangential and tensile stresses. The honey can only be lifted by a tangential force exerted by the knife's surface, which must be transmitted through adjacent layers of the honey. The stretching of the stream as it leaves the knife gives rise to tensile stresses across horizontal sections. These make the speed of falling much less than if the honey had been falling freely. Though this honey stream shows us something about the properties of viscosity, it doesn't give us any physical insight into the relative importance of viscosity and inertia. A similar set of experiments done with a controlled jet entering a quiescent mass of the same fluid can give us such an insight. In defining Reynolds number, the appropriate length and velocity to be used are the diameter and the velocity of the jet as it enters the fluid. Here the fluid is syrup, and the Reynolds number is 0.05. At this low Reynolds number, the jet hardly penetrates at all. Now let's repeat the experiment using different fluids. The other three boxes contain glycerine, glycerine and water. Each jet will be driven by this piston, and the velocities will be identical. This glycerine jet penetrates to a depth of a few diameters. At this Reynolds number, the jet penetrates many diameters. The tangential force acting on the outer surface of the jet is insufficient to reduce its velocity very much before it reaches the bottom of the box. This jet becomes turbulent. Here, for comparison, are the four situations.
So the cases that you saw in the video can be generalized in this picture. And here, the Reynolds number increases as you go from left to right. So of course, the case on the very right of this figure is an example of turbulent flow. But we are going to talk more about the cases which are towards the left of this figure. So the first one, where the Reynolds number is very close to zero, that is a classical example of Stokes flow. So we are going to restrict ourselves for the cases where the Reynolds number is very small. Let me begin this lecture by writing out the Cauchy momentum equation for liquids. So in this Cauchy momentum equation, we can identify the different parts. The term on the left-hand side is sometimes referred to as the inertia forces, which is basically the acceleration term. On the right, we have the pressure gradient term, and the second term on the right is the viscous stress term. In fact, this is the divergence of the viscous stress tau. And this viscous stress tau for Newtonian liquids can be written as 2 mu times the strain rate tensor S, where S is nothing but the symmetric part of the velocity gradient tensor. Now, once we make certain assumptions, namely that the velocity field is divergence free, which is to say that the fluid is incompressible. Furthermore, if we assume that the viscosity is constant, that is, viscosity is not a function of the spatial coordinate x, then we can write this divergence of viscous stress term as mu times the Laplace of velocity term. So note that we can only write the divergence of viscous stress as mu times the Laplace of the velocity field if the velocity field is divergence free and the viscosity is constant. So if we put in these assumptions, then we get a simplified version of the Navier-Stokes equation, which is, so in this lecture, we are going to work with this simplified form. So now let us try and non-dimensionalize this Navier-Stokes equation. But before we do so, let me remind you about the dimensional analysis lecture. If you remember, there we introduced some non-dimensional numbers, and the way we reached to those numbers was by identifying the relevant parameters of the problem and then trying to create some non-dimensional groups using the Buckingham Pi theorem. What you will see in the coming few minutes is that we will reach to a similar non-dimensional number. In fact, we will reach to the Reynolds number, but we will do it in a slightly different way. In fact, this is another way of coming up with non-dimensional numbers in fluid mechanics. That is by non-dimensionalizing the Navier-Stokes equation. So for that, let me introduce some velocity and length scales in the system. So let's say that U naught is the velocity scale, L is the length scale, and rho is the density scale. We can always form a time scale using the length scale and the velocity scale. However, note that the moment I write my time scale as L over U naught, I'm assuming that U naught times T naught by L is of the order 1. Of course, for the cases where this is not true, you will get another non-dimensional number, which is precisely U naught T naught by L. However, if you choose the velocity and the length scales wisely, then you can always define a time scale which is L over U naught. So what we are going to do is we will replace Ui by Ui tilde times U naught. We will replace T by T tilde times T naught, and we will replace uh, the length scale, the coordinate xi by xi tilde times L. Furthermore, we will replace P by P tilde times P naught. I will talk about this P naught in a minute. Once we do this, what we get is, of course, you should verify that at every step of the calculation, the equation is dimensionally consistent, which you can already see from this equation as well. Now, let us multiply the whole equation by L square by mu U naught. I'm going to drop the tilde from this equation just for the sake of simplicity. Now, something interesting happens. You can immediately identify this term as the Reynolds number. And in fact, now the equation reads, and as we promised in the beginning of this lecture, that we are going to talk only about the cases at low Reynolds number. And therefore, the left-hand side of this equation will vanish, which implies that the right-hand side should also be equal to 0. Now, if I choose a pressure scale, which is it is remarkable how, by selecting the right pressure scale and the right velocity and length scales, I get to an equation which is universal. So right now, this equation that the gradient of P is equal to the Laplace of U is a universal equation for low Reynolds number in the sense that this does not depend on any parameter of the flow. So this simply says that a variable p, its gradient, is equal to the Laplace of a velocity field u. It is interesting that we can, once we solve this equation, it using the proper boundary conditions, the solution that we are going to get will be valid for all Reynolds number, provided that the Reynolds number is small enough. Of course, this universal solution that we are going to get will be in the non-dimensional pressure and the non-dimensional velocity space. So basically, it will be in PL by mu u naught and u by u naught space. And if you want to scale it back to the real units, then we need to multiply the pressure by mu u naught by L and velocity by u naught and the length scales by L. So this brings me to the Stokes equation, which is that the gradient of pressure is equal to the Laplace of velocity field. Of course, in the non-dimensional pressure and velocity space. Now, this is the point of lecture where someone from the audience always gives me the question that why did we choose the pressure scale as mu u naught by L? And since we don't have an actual interactive class, I'm just going to assume that some of you might also be thinking about the same question. Till this lecture, we have been using pressure scale as rho u naught square. So what changed? Why are we using a different pressure scale for this problem? So for that, instead of just giving you the answer, let's do a small exercise. So what we are going to do is instead of using the pressure scale as mu u naught by L, we will use the pressure scale as rho u naught square, and let's see what will happen. So if we start from this equation, and instead of putting P naught as mu u naught by L, let's put P naught as rho u naught square. So if we do that, what we get is, so I can rewrite this equation as Reynolds times. Now if I take the assumption of that the Reynolds number is very small, then the entire left hand side of this equation vanishes, and then I'm simply left with an equation which says that the Laplace of u is 0. Now this makes the flow really boring because we have no driving force in the system. So the flow is usually driven by the pressure gradient, and as we see that the pressure gradient has a factor of Reynolds multiplied to it, it goes to 0 if we assume that the Reynolds number goes to 0. And this is of course not how we will describe the Stokes flow. And the reason is that in for Stokes flow, we assume that the Reynolds number is very small, which means that the that this number rho u naught L by mu is very small, which is to say that this rho times u naught is way smaller than mu over L. Now, if we multiply both sides by u naught, what we get is that rho u naught square is way smaller than mu u naught by L. And therefore, we cannot use rho u naught square as our pressure scale. So using rho u naught square as our pressure scale is incorrect in a way that we have another pressure scale in the system, which is mu u naught by L, which is way larger than rho u naught square. All right, after that small digression, let's come back to Stokes' flow. So we have this universal equation which says that the gradient of P is equal to the Laplace of velocity field u. So we can solve this equation by using one of the following two ways. The first is by taking a divergence of this equation. So once we take the divergence of this equation, what we get is the divergence of the gradient of P is equal to the divergence of the Laplace of u. And if we use the Cartesian tensor notation, it is easy to show that this is nothing but the Laplace of P equals the Laplace of divergence of u. And since this is an incompressible flow problem, the right hand side of this equation is 0. And so we end up with Laplace of P is 0. And this equation can now be solved by using the boundary conditions for pressure. Alternatively, what we can do is to take the curl of this equation. Now, if we take the curl of this equation, what we get is that the curl of the gradient of P is equal to the curl of the Laplace of U. Now, the left-hand side of this equation is curl of a gradient of a scalar field, which, as you know, is zero. So what we get is that the curl of the Laplace of U is zero. And if we know the velocity boundary conditions, we can then solve this equation. But this equation looks a bit scary. So what we are going to do is to simplify this further. Now, if I define a vorticity field, omega, as curl of U, then we can show that this equation, curl of the Laplace of U, is nothing but minus curl of omega, which by further manipulations can be shown as equivalent to the Laplace of omega equal to 0. As you can see, I have skipped a few intermediate steps. So what I want you to do is to use Cartesian tensor notation and then fill in those steps and let me know if you don't get those. What I'm going to use next is that I have this simplified equation which says that the Laplace of the vorticity field is 0. Now let us look into a special case of the Stokes flow, which is the 2D Stokes flow. So wherever we have a two-dimensional incompressible flow situation, we can define a stream function psi. And if we do that, the u component of the velocity is nothing but del psi by del y, and the v component of the velocity is nothing but minus del psi by del x. And you can see that the moment I define my velocity field in such a way, the divergence-free velocity condition is always satisfied. Now, the x component of the vorticity is going to be 0 because we have a 2D flow, and similarly, the y component of the vorticity is also going to be 0. Whereas the z component of the vorticity is defined as following. And if we plug in the definitions of u and v, what we end up getting is, so we get that the z component of the vorticity is nothing but negative of Laplace of psi. If we plug this in into the Stokes equation, which was that the Laplace of the vorticity field is 0, and if we plug this in, so then what we get is that the Laplace of the Laplace of psi is 0, which means that the nabla to the power 4 of psi is 0. So what we have is a fourth order partial differential equation, which will give us solutions to the Stokes 2D problem, provided that we use the correct boundary condition. Now, this fourth order partial differential equation might look scary to you, but let me remind you that we have seen similar equations before, and that was for an inviscid potential flow. There, of course, we had that the Laplace of psi is 0. So this was a second order partial differential equation. What we have now, so let me call this viscous Stokes flow. So what we have for a viscous Stokes flow is that the fourth order derivative, the fourth order Nabla operator applied to psi is 0. So this is a fourth order PDE. So one thing is very clear from this comparison is that we need more boundary conditions. And then secondly, all solutions of Laplace of psi equal to 0 are also solutions of a nabla to the power 4 of psi equals 0, because we can always write this the second equation as Laplace of psi equal to 0. So now we are going to look into some flow problems where we encounter such equations, and we will start with a recall of flow in a corner. So the situation that we had for such a flow was this, that there were two plates at an angle alpha, and then we solved the flow inside this region. And for that, we had to solve this Laplace of psi equal to 0. Of course, the boundary condition would read that the perpendicular, the normal velocity on this plate is 0, And also the normal velocity on this plate is also zero because both these plates are impermeable in nature. Furthermore, we can identify that to the leading order, the solution of this situation can be determined without reference to a solution of the global problem, because for sharp corners, the flow in this region should be self-similar. So we can define a self-similar ansatz, which is a r to the power lambda f theta, and then plug this in into the Laplace of psi equal to 0. And then what we end up getting, after applying the boundary conditions, of course, is that psi is equal to a r to the power lambda n sine lambda n theta, where a is simply the magnitude of this psi function. And then we get a flow situation which looks like this. So the streamlines of this flow looks like this. So this was the solution of a second order partial differential equation, that is Laplace of psi equals 0. So let me first give you some examples of such a flow. So here, this person is painting. So this is like some paint, and he's using a technique called a scrape painting. Of course, the liquid used in this painting is not Newtonian, but nonetheless, it is quite viscous. Furthermore, another daily life example where we can encounter Stokes flow is when we plaster our walls. So you see this plaster is being applied on this wall using this equipment. So let us try and draw the schematic of such flows. So in both the flows, what we saw was that we had a flat surface which was horizontal in case of painting, and it was vertical in the case of plastering. And there was another plate which was at some angle alpha, and then this plate was moving with a velocity u naught. And as this plate moves with a velocity u naught, it carries the viscous liquid along with it. So such problems are generally referred to as the Taylor-Scraper flows. In this, a solid plate is used to scrape a viscous fluid from a solid surface. Of course, if we look into the frame of reference of the scraper, what we get is the following situation. We get that the bottom wall is moving with a velocity u naught, and then this wedge is the scraper is stationary. And I can immediately tell you that the velocity, the streamlines in the corner, which will look like this. And as the name suggests, this problem was studied by G.I. Taylor in his famous paper called On Scraping Viscous Fluid from a Plane Surface. And I will provide this PDF on Canvas. And if you're interested, you can look into this original paper by Taylor. So now, if this corner between the scraper and the wall is indeed sharp, we can again expect there to be a self-similar solution for this problem. And then we can define the stream function psi as ar to the power lambda times f theta. So this ansatz is similar to what we used for the inviscid flow in a corner. But unlike the inviscid case, in this case, we already know that the velocity field is u naught. And if we do a dimensional analysis, we can argue that the lambda in this case should be equal to 1 and a should be equal to u naught. This is because psi has a dimension of meter square per second, and the only way that is going to be possible is if a was u naught and lambda was 1. Alternatively, if we go in a more formal way, we can also derive the same result. So UR is 1 by R del psi by del theta, which will be A by R to the power lambda, F prime theta. Now at theta equal to 0, this UR should be equal to minus U naught, irrespective of the value of R. And this is because the bottom plate is moving to the left with a velocity U naught if we sit in the reference frame of the scraper. What it gives me is A times R to the power lambda minus 1 f prime 0 is equal to minus u naught. Of course, we are going to assume that this f is a function of theta, and furthermore that the f is dimensionless, so f does not have any dimensions. So if we do that and we want this equation to be independent of r, then clearly lambda should be equal to 1 and a should be equal to minus u naught. And therefore, the answers that I get for this situation, psi as a function of r comma theta, is nothing but minus u naught r f of theta. Now, you need to plug this answer into the Stokes equation in terms of psi, which was nabla to the power 4 applied on psi is 0. Once you plug this in, you will get an ordinary differential equation, and I'm simply going to write out that equation. So now we have a fourth order ordinary differential equation, and this equation is linear. This equation will have a solution which goes as f theta is equal to. Now in this solution, you can identify that the terms with a sine theta plus c cos theta are harmonic in nature, and they are also solution of the Laplace of psi equal to 0. Whereas the other two terms, b theta sine theta plus d theta cos theta, are biharmonic in nature, and they come from the fact that we are solving a fourth order uh, ordinary differential equation. In order to get the values of a, b, c, and d, we need to plug in the boundary conditions. For the boundary conditions, what we have is that at theta equal to 0, u theta, which is nothing but minus del psi by del r, is 0. And this is the no penetration boundary condition. So this will translate to the boundary condition for f, which says f0 is equal to 0. Furthermore, at theta equal to 0, ur, which is equal to minus u naught, and continuing from our previous argument, this will give the condition that f prime 0 is equal to 1. This is of course the no slip boundary condition. Now at theta equal to alpha, u theta will again be equal to 0, which means that f alpha will be 0. Furthermore, ur will also be equal to 0, which means that u prime alpha will also be equal to 0. So we have four boundary conditions, namely that f0 equal to f of alpha equal to f prime alpha equal to 0, and we have f prime 0 equal to 1. So we can plug these boundary conditions in and then find the value of a, b, c, and d. If we do so, what we get is psi of r comma theta is nothing but. So this is the general solution for any angle alpha. Let us consider a special case which is for alpha equal to pi by 2. Once we simplify, what we get is, and this you can always visualize this stream function, and it will look like this. Of course, the bottom plate is moving to the left with a velocity u naught in the reference frame of the scraper, which is vertical in this case. So one of the important quantities that we can calculate in such a flow is the amount of force being applied on the moving plate. And you can do that if you know the surface stresses on this plate. And once you know the velocity field, you can easily calculate these stresses. I have given the expression over here. Now, one important feature of this expression is that at r tends to 0, these stresses diverge. So for r goes to 0, this both t theta theta and tr theta will go to infinity. And this apparent singularity is avoided by considering the fact that this scraper is always a certain distance over the plate. That is to say that there is a tiny gap between the scraper and the moving plate. So this was one of the questions that you had in your working class. So now is the time when I urge you to go back to the working class and try to solve that problem. So here I'm going to visualize the magnitude of the stress as a function of the angle alpha between the plates. And as you can see, as alpha goes to 0, this stress, it diverges, it goes to an infinite value. Whereas when alpha goes to pi, this stress, it vanishes. Now you can visualize this in a more everyday context is while you are plastering the wall, then we always try to keep the shovel at an acute angle with the wall. And this is to make sure that you have enough force being applied on the plaster so that you get a smooth finish to the plaster, and that the plaster reaches to the tiny holes that might have formed in the wall. So while plastering, we keep the shovel angle at an acute angle, and the reason is for a Taylor scraper flow, the stresses are really high as you go to acute angles. On the other hand, if you try to do the scrape painting, then at that point, the painters usually hold their paint scrapers at obtuse angle, and that is to minimize the effort in order to apply paint on the canvas. So you can appreciate how important understanding Taylor scraper flows is while painting or plastering the walls.